Hey guys, welcome to week 4 recap. I know the information that you looked at this week was a bit difficult. I understand that, but it's an important part of statistics, and I wanted to give you a different view versus kind of what you may be used to seeing. So I'm just going to jump right into things to go ahead and get just to get the recap going. So I'm going to start with probability because that's essentially what we're talking about. Probability is a complex but essential concept for understanding inferential statistics. Okay, point blank and period. We all have a notion of what probability means. That's generally where you see the likelihood or probably or there's a good chance type thing in problems or worksheets or even a statistical article or articles in general in statistics. And when you hear doctors or the clinicians talk about recovery or whatever the case may be, probability is used everywhere. So we use probability as a means of prediction. For example, there is a 50% chance of recovery, or this operation has a 75% chance of success. Statistically, we can view probability as a system of rules for analyzing a complete set of possible outcomes, or what we also call a sample space. So, for example, a sample space could represent the two sides of a coin or six face on a die. And I'm using this because this is what you often see when we kind of describe probability for teaching purposes. An event is a single observable happening or outcome, such as the appearance of tails on the flip of a coin or a 3 on the toss of a die. A sample score or a sample space could also be a set of IQ scores for all students in a given school system. These are just examples. But probability is the likelihood that any one event will occur given all the possible outcomes. Now, you've seen a lowercase p already, and we've already talked about it being related to probability. So within probability, we use the lowercase p to signify or express the chance. And it's expressed as a ratio or a decimal. So, for example, the two possible outcomes for the flip of a coin. The likelihood of getting a tails on any single flip will be 1 of 2, or 1 divided by 2, or 0.5. Therefore, we say the probability of getting a tails is 50%, or p equals 50. Now, suppose you want to know the probability of getting a 3 when a die is thrown. The sample space is the set of 6 faces of the die, or 6 possible outcomes. So therefore, the probability that you will roll a 3 is 1 out of 6, or 1 divided by 6, or p equals 1.67, because there's only 1 3 on a dice, so therefore you can only roll it once. Now, looking at the opposite, the probability of not rolling a 3 is 5 out of 6, or 5 divided by 6, where p equals 0.833, because there's 5 chances to not roll a 3 on a dice. Okay? Now, for an event that is certain to happen where p equals 1.0, and we're going to use the same example that we used previously here. Okay? So let's say, for example, if you toss a die, the probability of rolling a 3 or not rolling a 3 will equal 1, because you have p equals 0.167 plus 0.833. Now remember that 0.167 comes from the 1 of 3. Oh, I'm sorry, the 1 of 6. The 1 of 6 chances to roll a 3. And the 0.833 comes from the 5 out of 6 chances of not rolling a 3. These are considered two mutually exclusive events because they cannot occur together, and because they represent all possible outcomes. Therefore, the sum of their probabilities will always equal 1. And it's important to understand that probability is predictive, essentially. That's what I'm trying to get across here. And it reflects what should happen over a long period of time and not necessarily what will happen for any given trial or event. So like when you see a surgeon that says an operation has a 75% chance probability of success, it simply means that in the long run, for all such cases, 75% can be expected to be successful. Okay? Now, we're gonna look at probability and distribution of scores and where this fits in. This chart should look familiar. We have standard deviations here, and then you have the mean. As you know, the symbol means mean, okay? Probability can be applied to distribution of scores. Suppose you had access to data for height of all adult men alive today. That distribution of million of scores should fall to fit a normal curve. This is a normal curve. If it's not more towards the left or more towards the right, then it's normal. If it falls more towards the left or more towards the right, then it's considered skewed. If it's skewed to the right, that's considered positive. If it's skewed to the left, that's considered negatively skewed. Okay? Just a small recap. Okay, so again, this is a normal curve. So, suppose that the mean height was 69 inches. This is the mean. With a standard deviation of 3 inches. Now, what if you select one man at random from this entire population? What is the probability that the man you select will be between 66 and 72 inches? 66 and 72. And the reason why we're saying 66 and 72 is because it said the standard deviation is 3 inches. And this is within one standard deviation. Well, like we've talked about in class, we know that the range within this one standard deviation represents 68.26 of the population. Okay, that means that approximately 68 out of 100 men can be expected to be between 66 and 72 inches. Therefore, you have a 68% probability, or p equals 0.68, that any one man you select will fall within that range. Now, let's say you wanted to randomly select a man or find a man that would fit, that would be 78 inches. Okay, or taller. We can say or taller too. Now that's plus 3 standard deviations above, or plus 3 standard deviations and above at this point. And as you see here, that's 0.13. So the chance of picking a man that's 78 inches or taller is 13% of the total distribution. So that's kind of how that looks. Okay, so let's move on now that you have another basic understanding of probability that I've added on top of to everything that you've already read. Let's go on to one of your topics that everyone is kind of having some issues with, and that's binomial distribution. Okay. In many cases, it's appropriate to summarize a group of independent observations by the number of observations in a group that represent one of two outcomes. Okay, that's why we use binomial distribution. The binomial model is used when there are two possible outcomes in a situation, hence the bi. So let's say we were interested in looking at the effect of knee angle or knee extensor strength. Well, in that case, you would probably use a manual muscle test, and that has positive and negatives. Well, now those are your two outcomes, and that's where we're looking at. And we're looking at success or failure, positive or negative, or those type of things. Whatever it is, it has to be discrete. They're all discrete outcomes, and this model allows us to compute the probability of observing success. Binomial distribution describes the behavior of a count variable x if the number of observations n, the letter n, is fixed. 2, if each observation is independent. 3, if each observation represents one of two outcomes, so either success or failure. And 4, the probability of success, P, is the same for each outcome. Now, this is the binomial distribution model. It's using factorials. I'm not going to go into detail about this because I'm more so showing you this so that it's not unfamiliar when you're looking at it. And some studies will use this. This study, which I am providing to you, is one of the studies, occupational therapy studies, that actually did utilize a negative binomial model because it was looking at success and failures for stroke-related disabilities. And I think specifically, if I remember correctly, they were looking at falls. So this is, if you're interested in seeing where it kind of fits in the context of your clinical work, this is an article that you can read and get a somewhat of an understanding about. At least it gives you an idea of what you're looking at. All right. So just kind of going back to what I said earlier. So for the binomial distribution model, there are 3 assumptions that you should consider. If replicated, only 2 possible outcomes are available, success or failure. If replicated, the probability of success does not really change. And 3, replication is independent. So back on slide 7, I mentioned that the binomial distribution has discrete outcomes. Okay, so let's talk about this a little further. All probability distributions can be classified as discrete probability distributions or continuous probability distributions. I know we probably thought these words would disappear eventually, but they don't. They're integral within statistics. And depending on whether they define probabilities associated with discrete variables or continuous variables. Either way, these are the only 2. So if a variable can take on any value between 2 specific or 2 specified values, it's called a continuous variable. Otherwise, we call it a discrete variable. And we know some of the examples already, like the number of children, the number of languages one person may speak, or the number of people in a class, and specifically maybe OT 540. Okay? Sorry, I'm quiet because I'm thinking about what I want to say next. So I guess I should mention that we've only previously really talked about discrete data and continuous data as variables. But just like variables, probability distributions can be classified as discrete or continuous as well, which is why you're seeing this so much within this section this week. So if a random variable is a discrete variable, its probability distribution is called discrete probability distribution. Okay. An example of this could be, suppose you flip a coin 2 times. Okay. This simple statistical experiment can have 4 possible outcomes, and I should probably write it out. So you could either have HH, you could have HT, or TH for heads, tails, head, or you could have, what's the last one? Tails. Now, let's see, I should probably do Now let the random variable